Hi all, welcome back to System Verilog sessions. In this video, I'm going to show you the examples for implicit bins and explicit bins. In the last video, I already explained what is implicit and explicit bins, right? So in this video, we will see the examples, okay? I'll also show you how to generate the coverage report in EDA Playground. For that, the first thing is in the tools and simulators, you need to select Aldec Revara Pro Simulator. Okay, so this will support you to see the coverage report. Other simulators will not support. Okay, and after that you need to select this option, use run.do tickle file. Okay, so here you need to select this because you are going to add the run.do file in the here. Okay, so here we are going to add the run.do file. We will see what is there in the run.do file. So this file will help you to generate the coverage report. Here we have 6 commands. The first one is vsim plus xs plus r. So this command will launch the QuestaSim simulator, and this plus xs plus r option will provide you it will provide the read access to all signals. Okay, and the run hyphen all means it will run the simulation until all the processes are completed or until $finish or $stop is called. And ACDB save means it will save the coverage data that is collected during the simulation. Okay, ACDB means advanced coverage database, and ACDB report means here that ACDB file will be generated, coverage report will be generated, and hyphen db fcover ACDB, this is the name of that input coverage file, and hyphen txt means the coverage report will be in the text format, and hyphen o code.txt hyphen verbose, this means the name of the output coverage report which is in the text format, and verbose means the detailed information will be provided in the report, and exec execcat code.txt. So this command will help you to display the coverage report in terminal or log. Okay, and exit means it will exit the simulation. So you can copy this command and put it in the run.do file. Okay, same command, there is no change. Now we will see the first example, implicit bins. In the last video, I forgot to mention this point. Okay, so here I will be explaining that maximum 64 auto bins will be created by default. That means if you don't provide this auto bin max value, then by default only 64 auto bins will be created. Okay, irrespective of the data width, only 64 auto bins will be created. So here you can see if variable is less than or equals to 6 bits, that means 2 to the power 6 is 64, right? So if the variable is less than or equals to 6 bits, then auto bins is equals to 2 to the power variable data width. Okay, so if your variable is 3 bit, 4 bit, 5 bit, then auto bins will be 2 to the power 3, 2 to the power 5, 2 to the power 6. So if the variable is greater than 6 bits, for example, your data is 8 bits, 7 bit, 9 bit, 10 bit, then only 64 auto bins will be created if you don't provide the auto bin max value, because by default only 64 auto bins will be created, right? So only 64 auto bins will be created, and each bin has a 4 values in case of 8 bit data. So how we are telling that, here you can see 2 to the power 8 by 64. You need to divide the this total auto bins by 64. Okay, for example, if your data is 8 bit, then 2 to the power 8 is how much? 256. You need to divide by 64 because maximum is 64 bins, right? So in the one bin, how many values it can have? 4 values. Like that you need to do. Okay, so this is one thing, and you can change that maximum value by using this option dot auto underscore bin underscore max is equals to 128 or 256, like that. Okay, so there are many options in the coverage, we will see in upcoming videos. Okay, so as of now you can just know that the default value is 64 for auto bin max. Okay, and now we will see the example, module functional coverage. Here the same example, whatever I have explained in the PPT, same example here I have taken. Okay, address data enable, and here the cover group is there, all the 3 cover points, address data, and by using the cover point keyword, I'm declaring the variable as cover point. Okay, now these 3 variables will be covered, and here I am using one option dot per underscore instance. So here I was telling you, right, auto bin max, how I have to use this, by using this option dot auto underscore bin underscore max is equals to 128, 256, like that. Similarly, one more option is there, option dot per underscore instance. So this will help you to see each instance of the cover group. That means each auto bins you can see in the report. Okay, for address, how many auto bins will be created, all the each instance we can see by using this option dot per instance, and you have to provide the value as 1. Okay, after that I'm creating the that CG cover group handle, C underscore group CG, and by using the new operator. Then here I'm generating the stimulus. I'm generating the value for the variables, right? How many times? 20 times I'm giving the value. And here I'm calling the cg.sample. This time I'm not using any events, any clocking events. I'm just using the cg.sample. So if I'm using any clocking event, then no need of calling the cg.sample, right? Because at that event it will be sampled, but here we don't have any clocking event. I'm calling cg.sample. So for each value, each repetitions, I'm calling the cg.sample. Okay, whenever the value changes for address data enable, I will be calling cg.sample, so that all values will be sampled, and after that I'm displaying. So now I will run the code. Here you can see all the commands vcm access plus r, all the commands we can see here. Run all. After that our display statements are displaying here. Okay, address for all the values 20 times, and after that it is saving the coverage database and report is generated, right? Here coverage report code.txt was generated successfully. Here it is displaying in the terminal. See, you can see from here. Okay, so this is for cp1. What is cp1? This is the cp1 cover pointer name, right? Address is 4 bits, so 2 to the power 4. How much? 16. 0 to 15. 0 to 15, total 16 auto bins are created here. And how many? This is the, like, at least it has to hit for one time. Okay, at least one time it has to hit. If it hits at least for one time, then it will be covered in the coverage calculation. Okay, so here you can see auto bin of 0, it has covered for one time. So this will tell you how many times the value has been covered. 1 0 1 3 1 2, like this. Okay, here you can see cp2. CP2 for data is 3 bit, right? 2 to the power 3 is 8. 0 to 8 auto bins are created. Here you can see 3 4 3 2 4 3 1, right? Total how many values, how many times you are repeating? 20 times. So 4 3 7 7 3 10 10 12 12 4 16 16 3 19 19 1 20, total 20 values, right? So this many times the values are covered, and total coverage is 87.5%. And for cp3, 0 and 1, so because it is a single bit, 2 to the power 2 to the power 1 is 2, so 2 bins are created here. 9 11, so 1 1, 100% covered. All the possible values are 0 and 1, so it has been covered, so 100%. So the total coverage will be here, you can see 83.33. This is the total coverage, 83.33 for 100%. Okay, so this is how you can see the coverage report, and I'll show you the auto bin max effect. Okay, here what I'll do, I'll take address as not this one, I'll take data as 8 bit. Okay, this is for cp2 data. Here you can see in each bin how many values it has. 0 to 3, 0 1 2 3, total 4 values, right? Here we have calculated 2 to the power 8 divided by 64, because auto bin max value is 64 here. That's why each bin has 4 values. Now what I will do, I'll set the value for auto bin max. I know that 2 to the power 8 is 256. Here option dot auto bin max is equals to 256. Okay, now I need to see here. I'm getting bin auto 255, right? Single bins are created from 0. here from 0 to I'm getting 255. That is nothing but 256 auto bins are created by setting the auto bin max value, right? So this is the difference. By default only 64 auto bins will be created. At that time each bin will get, we need to divide the 64 by 2 to the power how many data bits it has, original data bits of the variable. Okay, 2 to the power 8 by 64. If your variable is 2 to the 10 bits, then 2 to the power 10 by 64, like that, so that we can get to know how many values each bin has, like that. Okay, so this is one thing. And next example, we will see the next example. Okay, explicit bins. This is also same as before, but bins are declared. So address data enable C group option dot per instance. Here I am declaring I'm giving some values for each bins. Okay, for address I am creating three types of bins. One is scalar bin. Here I am giving 1, 10, 12, and in B2 is a vector bin. So in the video for this example, what I told, total 2 bins will be created, 2 vector bins will be created, right? But it is not like that, sorry for that. Here total how many elements it has, from 2 to 9 how many, 2, 3, 4, 5, 6, 7, 8, 9, total 8 values. Then comma 11, so total 9 bins will be created. Okay, B2 of 0 to B2 of 8, total 9 bins will be created. So it's not like 2 elements, 2 to 9 is 1 and 11 is 1. It's not like 2 elements, total 2 to 9 and 11. Okay, total 9 elements are there in B2. It's like that. Okay, you need to consider the range also in the vector bins when the size is not provided. Okay, we will see in the report, you can understand better. Then bins 0 to 7, here I'm giving one name. Here I'm not just giving b1 b2, I'm giving 0 to 7 and 4. Here I'm declaring the size, so that means only 4 bins will be created, 0 to 7. And I told you it will be divided, right, if it has a even numbers. 0 to 7 means total 8 values, so each bin will get 2 values. And for data, b1 is equals to 5 down to dollar. So what is the dollar means maximum range. For what is the maximum range for data? Data is 3 bits, right? So 3 bits means 2 to the power 3, 0 to 7, 8 values total. So dollar is nothing but 7 here, 5 down to 7, 5, 6, 7. Okay, so in the b1 only one bin will be created for 5, 6, 7 values. And bins b2 is vector. Here you can directly say 3. 3 elements are there, 3 bins will be created, because there is no range here to count, right? So only 3 elements are there, 3 bins will be created. And bin others, so here I'm giving one keyword default. So when you give the bins as default, then whatever other values, so here you have declared 5 to 7 and 2, 3, 6. Other than this, whatever the values are there, that value will be counted in others bin. Okay, so here others default means the other values which are not covered in other bins. Okay, so this is the default keyword. You can use it for counting the remaining values. Okay, and for the n variable, n is a single bit and I'm just covering the value 1, so I want to check whether 1 has hit or not. Okay, 1 has covered or not. We will see. So here CP1 is the first cover point for address, right? How many types of bins we are creating? 3 types of bins, B1, B2 and 0 to 7. So B1 is a scalar bin, right? So only one bin has created, B1 and 2 times that value has hit within this 1, 10, 12. So within this range 2 times the values are covered. Okay, B2 is vector bins, right? So here how many elements we have? We have total 9 elements. 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 to 11, right? 2 to 11 how much? 9 elements. So 9 bins are created. And how many times the values have been hit? Here you can see that. Okay, and after that 0 to 7. So 4, it's a vector bin only, but size is declared. So 4 bins will be created, 0, 1, 2, 3, right? And how many times the values are hit? 1, 4, 3 times. So here it is showing this many times the values are covered, right? So we will check one bin properly. Okay, here I will take the maximum is 4 here, so I will check this one. Okay, bin 0 to 7 of 1. So this bin I will check whether the value is covered 4 times or not. Okay, so 0 to 7 of 1 means what? 0 to 7 of 1 means, so 0 to 7 of 0 means I'll get 0 and 1 in the first bin, right? And in the second bin 2 to 3 I'll get. So 2 to 3 means if if address has 2 or 3, then that value will be counted, right? So we will check in the display statement whether we are getting 2 and 3 for address or not. So here how many times 2 and 3 comes, you need to check. 1, 2, 3, 4, right? Total 3 and 2 how many times? 4 times. So here it is showing that 0 to 7 of 1 is 4 times. You got it? We will check here bin B1, which is this one, CP2. So B1 is 8 times, means 5 to 7, 5, 6, 7. Dollar is 7, right, for data, because data is 3 bits. 2 to the power 3 is 8, so 0 to 7. So 5 down to 7, 5, 6, 7. These three values are covered. We can see how many times it has been covered in the display statement. 5, 6, 7. This is for data. Here you can see 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7 times, but it was showing 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so total 8 times. 5, 6, 7 values are covered, total 8 times. That's why it is showing 8. And the total coverage is 92.857. Okay, and each cover point is here, CP1 is covered for 78.57 and CP2 100% and CP3 100%. So the total coverage is 92.857. So this is how you have to check the coverage report. And this is about the explicit bins. One more example I have. Okay, I'll show you that. So this is the example for cover group with clocking event. In the previous example, we have sampled the values by using the sample method, right? But in this example, we are not going to call the sample method. We just sample the values by using the clocking event. So how to use? Here you can see, here I have two signals, okay, mode and CFG. Mode is 2 bits and CFG is 3 bits, and here I am generating the clock, because clocking event means we need a clock, right, to sample the values. So how to write? In the cover group, here we have to give, after the name of the cover group, add passage clock. So here I am taking passage. That means for each passage clock, the values will be sampled. Generating stimulus will be sampled at passage clock. Okay, if you take net gauge, then net gauge clock, the values will be sampled. And here I am taking option dot per instance is equals to 1 to see all the bins. And here I have 4 cover points. If you see, I have 2 variables, but here I have 4 cover points, right? 4 cover points, right? So it's not like how many variables we have, that many cover points should be generated. No, it's not like that. Okay, you can generate any number of cover points. You can give the expression also. Here you can see. So I'll tell you what is the auto bins of the each cover point. Okay, so the first one is CP mode, cover point mode. Mode is 2 bits, so 2 to the power 2, 4 auto bins will be created. And after that, cover point CFG of 1 down to 0. So here you can see CFG is 3 bits, but here I am giving CFG of 1 down to 0. So if you declare the variable as like this, then it will take only 2 bits of CFG. CFG is 3 bits, but here you have declared 1 down to 0. That's why total 2 to the power 2, 4 auto bins will be created for this cover point. Okay, and after that CFG of 0. So here 0 down to 1 means 2 bits, and 0 means 1 bit, right? So 2 to the power 1 is 2. Total 2 auto bins will be created for this cover point. And the last one is expression. Here mode plus CFG. Here how many auto bins will be created? Mode is how many bits? Mode is 2 bits, right? Total, what's the value? 0, 1, 2, 3. Total 4 bins will be created for mode. And what is the value? What is the range of CFG? CFG is 3 bits, right? So 0, 1, 2, 3, 4, 5, 6, 7. So 0 to 7, total 8 values. So when you use the expression in the cover point, then the auto bins will be equals to the maximum data width, like 2 to the power maximum data width. What is the maximum data width in mode and CFG? CFG, right? Because CFG is 3 bits and mode is 2 bits. So maximum width is CFG. So it will take only unique values. Here you can see 0, 1, 2, 3, 0, 1, 2, 3. it's repeated, right, 2 times, so it will take only 1 time. That's why 0 1 2 3 4 5 6 7 total 8 auto bins will be created. You can just remember that number of auto bins in the expression will be equals to the 2 to the power maximum data width of the variables. Okay, here between mode and CFG has high number of data bits, that is 3 bits. That's why 2 to the power 3, 8 auto bins will be created. Okay, so for example, if you have 6 bits of CFG, then 2 to the power 6, because CFG is highest data bits, right? It has highest data bits. So you can just remember like this. Okay, the auto bins will be created for unique values, so it will not count the repeated values. So this is the one thing. And why I am explaining each cover point like this, because in interview they will give you the data width of that variable, and they will ask you how many auto bins will be created for the cover point. Okay, they may give you like this: cover point mode plus CFG, or cover point CFG of 1 down to 0, and they will ask you how many auto bins will be created. So that time you should be in a position to answer this question. Okay, because you need to understand how auto bins will be created. Okay, so for the explicit bins, it's not a problem. You can declare the bins with a size, or you can say if b1 is equal to some values, then you can say that is a scalar bin. Or if you give the size, then you can say that it is a vector bin of 4 or 5 or 6. Or you can, if the size is not declared, then you can tell by using the number of elements, right? But in the auto bins, it's not like that. So you need to understand that, and also remember the auto bin max value. Okay, so these are all the important things to remember in implicit and explicit bins. So here I'm instantiating the cover group, and here I'm creating the memory for the instance of the cover group, and here I'm generating the values for the mode and CFG signal. So here at the net gauge clock, I'm 5 times I'm repeating the 5 times I'm giving the values for mode and CFG. At net gauge clock, I'm generating the values, and I'm displaying the value here, and after that I'm calling the finish method. Now I will run. Here you can see for CP mode how many 4 auto bins, right? 2 to the power 2 4, and CFG of 1 down to 0. 1 down to 0 is 2. So 4 auto bins are created for this second cover point. Third point is 0 means 1 bit. So 2 to the power 1 is 2. 2 auto bins are created. And after that mode CFG. Mode plus CFG. Total I told you, right? 0 to 7. That is nothing but 8 auto bins are created. So for unique values. Okay, this is the one thing you need to remember. And here you can see total how many times I'm getting the values: 8 1 9 10 11 12. Total 12 values are covered, but I'm just repeating only for 5 times, right? How I'm getting 10 times? Because of that, here this is the clock I'm taking. You know that for each passage clock the values will be sampled, right? Even though if you are generating for 5 times, the clock will be it will be finished at 500 nanosecond. Right, here you can see once. Here 5 times values are generated. So I'm generating clock for each 20 clock cycle. The clock will be toggled, right? That means for one clock cycle it will take 40 seconds. So 40 nanosecond. So here you can see 40 to 200 nanosecond, 5 values are created. We are iterating for 5 times only, but after that the clock is still toggling, right? Because we are calling at what time? We are calling the finish method at 500 nanosecond. So here you can see stopped at time 500 nanosecond, because here only 200 nanoseconds are done. After that clock will be toggling. So we are calling the sample method at passage clock, right? So at each passage clock the values will be sampling. That's why after 200 nanosecond at each passage clock the values will be counting. For example, last value is 1. So 1 will be continued till 500 nanosecond. That's why here 5 values are there. After that again 200. So again 5 sets of value, 10 values. So total 400 is done. Then again 100 nanosecond is there, right? So you can just take 40 to 80. So 2 values, total 12 values. So you may not understand if I tell you like this, but if you display the waveform, then you can see how many values it has been covered in the waveform. Okay, total 12 passage will be generated in the waveform, and for 12 times the values will be sampled. Okay, that's why you are seeing 12 numbers. Okay, so these are all about the cover groups. We will see the transition bins in next video. Thank you.